Hi everyone, my name is Ram Musa, and today I'll be presenting our probabilistic approach to network telemetry. And this is really enabled by this trend that we have now of programmable hardware devices. We have a lot of different companies working on these, and surely enough, in academia we created a lot of cool systems with it. But it's not only an academic dream. So now we have large companies that are actually buying, for example, programmable switches and use them to replace the traditional ones. And one of the really killer applications for this programmability is network telemetry. And network telemetry is about figuring out what's going on in the network. So for example, we may want to ask, is there a congestion or a queue buildup somewhere? Do the passes taken by packets conform with the policy? Like maybe I want everything to go through a firewall or something. On the application side, can we increase the sending rate of some flow act without causing congestion or hurting the performance, right? So to that end, we can use telemetry. And for this, we have the INT protocol, or in-band network telemetry. So the way INT works is conceptually simple. We want to collect information from the network, and we can just add it to data packets, right? So let's say I want to know what is the path taken by a packet. Then I would need to collect the switch IDs. And the way this would work is that the first hop, and this can be either the end host or the ingress switch, it would take the packet and add to it something that's called the INT header. Now, this header tells the other switches on the path, we are collecting switch IDs, right? So now this first hop adds this header, adds its own value, it's called the metadata value, and sends the packet to the next hop. The next hop reads the INT header, figures we're collecting switch IDs, adds its own ID and forwards the packet, and so on. The packet goes all the way to the last hop that removes the INT information from the packet. So this protocol is transparent to the sender and receiver. And now we have this information, we can, for example, figure out the path, right? So let me give you a few use cases for INT. And the first is congestion control. So just like on the road, if you have too many packets going on a link at the same time, you're gonna get congestion. And congestion control is about tuning the sending rate to avoid congestion. And it turns out that the state-of-the-art congestion control, which is already running in production in Alibaba, is using INT to collect information. And this allows the end host to determine at what rate it can send without causing congestion, without overwhelming the network. A second use case is for path discovery. So the idea is that there can be many different ways to connect the source and destination. And here I want to know which path do my packets take, or which rules do they follow. More high level, I want to know if the path conforms to policy. And this is actually one of the use cases that Barefoot markets as their advanced network telemetry. A third use case is for network debugging. And the idea is that we may have, let's say, high end-to-end latency somewhere in the network, but we want to diagnose what is the problem. So we want to, for example, figure out which links or switches have high latency. We want to find out loading balances. If there are two ways to go to the same place, one of them is congested, the other is not, we want to know about it, we want to fix that. So all of these use cases you can do with INT, right? So it's really general. You can use it for a large variety of statistics. It's already running in production. I think all of the major switch vendors are now supporting it in their products, but it also introduces high packet overheads. And what I mean by that is each value that the switch adds more and more bits to the packet, right? So in INT, this is hard-coded to be 4 bytes per switch per telemetry type. And this grows multilinearly in both the path lengths and the number of telemetry types that we are trying to collect. So what's the issue here, right? So we have this high packet overhead, and the way this works is that if we live in a world without INT, you would send a packet and almost all of the packet would be the payload. You would need a small header for the routing, but that's it. Well, if you enable INT, then the sender would have to provision enough bits for the INT information so that it doesn't cause, it doesn't exceed the MTU and cause fragmentation and things like that, right? So we have fewer bits for the payload, and this means, for example, if we think of long flows, they would need to send more packets to transmit the same amount of information, right? So we ran an experiment in which we use a factory topology, a web search workload. So this is like the starting point for HPCC, this congestion control algorithm I mentioned. And we measured by how much the goodput of the long flows go down when we add this overhead, right? So here, normalized goodput means what is the reduction compared to running this flow alone. And what we saw is that even if you collect just one information, just one telemetry type, like you want to do path tracing, so you collect switch IDs, this already reduces the goodput by quite a bit. While algorithms like HPCC, this congestion control algorithm, actually requires slightly different values, so it reduces even more. And if you want to, for example, run HPCC while tracing paths, it would be even worse, right? So this sums up. And it may seem that this is a problem only for long flows, and maybe short flows that only send a few small packets should be fine. But the second issue with the iPacket overheads is they cause increase in the switch processing time. And the reason for that is if we have a switch and we have a packet with a fixed payload, then if we add these INT bits, it's gonna take more time for the switch to serialize and deserialize the packet, and it would add latency. And in our calculation, every telemetry type that you add to a packet on a 10G link would roughly add 1% to the processing time. A third problem, again, for these high packet overheads is the collection cost. And what I mean by that is we have our network, we have the collector that is supposed to get all this information. Now the switches would add this INT information and then send it to the collector, right? But that creates a lot of data, right? So it overloads the network, it creates high processing overheads at the collector, and more than that, state-of-the-art telemetry processing systems like Conflow actually assume that each packet carry a fixed byte-size amount of data, which is not the case in INT. So this motivated us to propose PINT, and the goal of PINT is to collect this telemetry information so they really care about while minimizing the bit overhead. And like in INT, we have this notion of values. So values can be one of the INT metadata type, but they can also be anything that is computable in the data plane. And the insight behind PINT, like the reason why we think that in many cases we can improve over INT, is that a lot of the applications don't actually need all of the data that INT collects. So INT gives you all of the per packet, per switch values, which you may not need, right? So we need some aggregated form of them. So for example, to determine the sending rate. And if we can do the segregation in the network, we can save a lot. PINT is implemented in P4, and it should be compilable to different programmable devices. Okay, so let me explain what types of aggregation PINT can do. The first is what we call per packet aggregation. And the idea is that we're going to have a packet going along a path. It's going to observe some value in each switch, and we want to output some function of these values. So for example, if these values are latency or maybe congestion signal, then we can track the maximum congestion signal and it would correspond to the bottleneck, right? And this is actually what we use for congestion control. We also have per flow aggregation, and the idea is that I'm going to have a flow, it's going to have multiple packets, they are all going to go through that path, and they're going to observe values. We have two subcases. The first is the static case, where the values are the same for all packets on a given switch. You can think of maybe like the switch ID or routing rule. And now what we want to do is we want to read out this information. For example, we want to discover the path. And what we do in PINT is we leverage the fact that the different packets are going to see the same switch ID, the same value. So we can do some coding and other tricks to reduce the amount of bits on each packet while still being able to recover the whole path. And the last case is the dynamic case where the values can be completely different. You can think of it as maybe latency measurements. And we still want to know things like what was the tail latency on some flow, on some switch, or what was the median latency, and so on. Okay, so the techniques we use in PINT, I'm going to talk about 3 here. First is we use global hash functions. So if you think about it, like if we want to run, for example, several queries, and we don't have enough bits to run all of them in all packets, we need the switches to agree what queries to run on the current packet. And this is done using a global hash function. So a function that all of the switches know, and we can hash on the packet ID and figure out what to do. A second technique is approximation. So if we have a numerical value, like maybe latency, we can approximate it. And then we introduce some error, but we can reduce the amount of bits. And if we think of this congestion control that I talked about, we can actually do randomized rounding. So with some probability, we're going to round it up, some probability, we're going to round it down. And across many packets, it's going to average out and cancel. And the third technique we're using is coding. So if we think of static things like inferring the switch IDs, we can actually use coding, and I'll tell you what I mean by that, to reduce the number of packets we need to read out, for example, the path information. So all of our use cases use different combinations of these techniques. And this allows us to solve the overhead issues. Because we have a lower overhead, we don't degrade the output as much as INT does by adding a lot of bits. We also reduce the switch processing time, and we use fixed size packet digest that allow us to be more compatible with processing systems and reduce the network overhead. Okay, so let me go over a couple of use cases. I'm going to start with congestion control. And congestion control, this HPCC algorithm is using INT to collect latency and queuing information, and this allows it to determine the sending rate. But if you look at the algorithm, what it actually does is it finds what was the bottleneck along the flow's path and determines by how much it can raise the sending rate without overloading this bottleneck. So in that sense, if we can identify the bottleneck, we can tune the sending rate. So what we do in PINT is we move the computation of the formula from the end host to the switches. We also use approximations, and now we can only track the maximum congestion signal on the packet, and we can do this with far fewer bits than HPCC does. And what happens as a result is we get improved performance on the long flows, because now we can send fewer packets to send the same amount of information. The second use case was for path discovery. So here, if I want to know the path, the values are just going to be the switch IDs. And the way INT solves that, it just adds all of the hop IDs to the packet, but now we want to reduce the overhead. And in our paper, we have a solution that allows you to do that with even a single bit per packet. But in today's talk, let's assume that I'm willing to write one identifier on each packet. Not all of them, just one. So if that's the case, what we can do is we can just sample one ID, right? So we can write each of these IDs in this example with probability 1 in 4. And this is actually doable because each switch can look at the TTL value. So for example, switch B can compute and know that it is the second hop on the path. And then we can run an algorithm called reservoir sampling to make sure that they are sampled with the same probability. And this is without knowing the path length, right? So maybe the first packet comes in, maybe it sampled the ATC and so on. So we get a bunch of these packets, and once we've seen all of them, we can terminate, and now we know the path. So the metric of how good an algorithm is for this problem is really about how many packets we need, right, before we can figure out the path. And in this example, this is what's called the coupon collector process. And it is known that if we have k hops, we would need something like k lambda k packets. So let me give you some intuition about this process. Right, so here, this is an example where we started from 25 hops, and the x-axis is the number of samples we collected, the y-axis is the expected number of missing hops, and you can see that it starts fast, but then it really slows down. And if we look at the first 40 packets, for example, we can already figure out in expectation 20 out of the 25 hops, but now the algorithm really slows down because now each consecutive packet is going to carry new hop ID with a probability of at most 1 in 5. Right? So this is going to be what we're going to try to improve, and we're going to do this using coding. And I'm going to give you some intuition about it. Let's say that I have this path of 2 hops. So the way the baseline would work is that the first packet would always carry some ID, like A, right? But now each consecutive packet is only gonna carry the other hop ID with a probability of 1/2, right? So on average, we would need 2 packets before we can figure out the path, or 3 packets overall. In contrast, think of what would happen if instead of always sampling, we would sample an ID with probability 1/2, and otherwise we would write the bitwise XOR of both identifiers. So what happens now is that if the first packet had an identifier like A, then we are more likely to terminate with each consecutive packet, because if we get B, then we're done. But also if we get A XOR B, and we already know A, then we can also infer the ID of B, and this is how we can reduce the number of packets we need. Right? But that was just a special case. Let me give you an actual algorithm. It's also going to make a couple of assumptions. One is we're going to assume that we know a ballpark number of how long the path is going to be. So maybe up to a factor of 2 or 3 should be fine. And the other is we're going to assume that each packet has an identifier that is unique across the network. Now, the way the algorithm works is that each switch would XOR its identifier with some probability. And the only tricky part is that the switches are going to choose whether to XOR or not based on some global hash function that is a function of the time to leave field and the packet ID. And the idea is that if a packet comes in, and let's say it was XORed by A and B, the collector can go and compute this function H for the previous TTL values and figure out it was XORed by the first and second hop. Right? So maybe the next packet got XORed only by C, maybe got unlucky on the third packet, no one XORed it, and so on. But the way this algorithm progresses is that we can actually use packets like the fourth one to infer new information, because we already know that the third hop had identifier C, then now we can know that the fourth hop has an identifier of D, right? So if we go back to this figure, and this is going to be just an intuition, but think of what would happen if after these 40 packets, we're going to switch from the baseline to the XOR algorithm, and we're going to set the sampling probability to be 1/5, 1 over the expected number of missing hops. Then what would happen is that we're going to get more likely to hit new information with each packet, and we're going to get a speed up compared to the baseline. But once again, it slows down, right? So there's no need to stop here. So we can switch to another XOR algorithm with an even higher probability and get another speed up. And while this may not seem significant, the baseline would need a lot more packets to finish this decoding. I will show that in a bit. So that was just intuition, right? We don't expect the switches to track the number of packets for each flow. So let me give you an actual algorithm. And this is going to run for every switch and each packet, right? So we're going to run the coupon collector algorithm with some probability. And otherwise, we're going to run a bunch of XOR algorithms, and we're going to choose which one and train them. And if I talked about global hash functions, then the switches are going to use a global hash function on the packet ID to figure out which algorithm or which layer it belongs to. And the XOR instances are different from each other in the sampling probabilities, like the previous slide suggested. And it turns out that if you optimize these parameters, we can actually bring the number of packets we need down from this scalar k to something that is almost linear in the path length. And this is what it looks like, right? So here, the x-axis is the number of packets, the y-axis is the probability for decoding. And you can see that the baseline and XOR have roughly the same performance, but our hybrid solution works much better. And this is especially evident in the tail, right? So if you want to decode, let's say 99% of the flows, you're far better off using our approach. Okay, so in the paper, we also have algorithms for dynamic aggregations, like if we want to estimate tail latencies. We have performance guarantees for all of our algorithms, and we also have support for concurrent queries. And what I mean by that is that we may want to run several queries at the same time. So we ran an experiment in which we use all three use cases concurrently, and we compare the performance of each to running this query alone without anything else. And what we saw is that using just 16 bits per packet, we can get a performance that is almost the same as running each of them separately. And we do this by scheduling different queries across different packets, once again, using global hash functions. So that is it. I'll be happy to take any questions in the Slack channel. Thanks so much for watching this.